But if you see this structure, this is the end of our sample. So you have at this point you have also longitudinal diffusion too. This is the, and as you see, diffusion rate through here are obviously more because you have more void aligned here rather than here. So as you see that you have cracks in this direction. One of the important mechanical property that they are dealing with, or the industry are dealing with, is that basically tensile strength of our material. We put our material for 1 year in the oven, and then we did the tensile at 180 degrees C and 200 degrees C. And you see the tensile strength is almost constant, so which means that the oxidation couldn't help basically the oxidation didn't affect the tensile strength of our material. So why that happened? We used assuming basically the Hooke's law, the Brita failure, since the only terms changes in this equation is just the matrix modulus due to the oxidation. So this is the distribution of matrix modulus. This is the surface of our material, and as you go in, you see when the matrix oxidizes, the modulus increases. But the thing is, since the oxidation is 100 microns, and compared to the whole structure is a small portion, it didn't change the whole tensile strength of our material. And as a conclusion, as we saw, we used the diffusion reaction equation to model our system, and it really works up to a certain time. And the glass fiber also acts as a barrier against oxidation of our carbon core, because our carbon core basically has more strength in that, and basically it mainly reinforces the material. And the alignment of fibers are really important because it's since the fibers are since the direction of oxygen penetration is vertical to the direction of the fibers, so it resists the penetration of oxygen through the material. And since the oxidation is so a small portion of our composite, it didn't affect the thermal degradation of our material. And I would like also to thank Composite Technology Corporation for their support. Thank you all. And
questions?
I have a fundamental kind of question. You're looking now at the effect of air, essentially, on the very center part of this composite wire.
Yeah.
Now that's surrounded by much, much more aluminum.
Right.
And that is aluminum alloy 0. That's very ductile.
Right.
And now how much oxygen and air do you assume got through the aluminum into that center core?
Yeah. I did basically the same experiment, and I put the actual conductor in the oven and just the core in the oven. And I measured the weight loss of just the core, and basically those were the same, which means that the oxidation, the wrapped aluminum didn't affect the oxygen could penetrate basically.
It could?
Yeah, because it's not fully wrapped around it, and the oxygen can penetrate through. If you see the
Is there open space?
Yeah, there are a lot of open space. Yeah. Yeah.
You know, on that conductor, I mean, I never looked at conductors before, but I noticed that the ACC looks like it's centered or somehow, it looks different than the ACR as far as the constituent.
Yeah.
Are they square or are they rectangular?
The trapezoidal.
Trapezoidal?
Yeah.
But they don't use anything to heat them or treat them in any way to get them to be...
To be what?
Yeah, to get them to fuse?
Yeah, I exactly didn't know how they wrap it because they sent it to Canada, and I exactly don't know to answer you. But
it looks fused as compared to the AC.
Yeah, but it's not fused. It's wrapped.
Yes,
you can take out with your hands.
Oh,
yeah,
okay.
it's not fused.
Okay. It must be their geometry that is such a nice wrap.
Yes.
I saw that you assumed that the diffusion coefficient is constant. Is that
no, the diffusion, because that's one of our assumptions. The thing is, we have a problem of measuring the diffusivity of, as you see, since the material changes, the diffusivity should change. So,
And you expect to change a lot because you're oxidizing by
yeah.
portion of
Yeah.
it.
One of the assumptions is I assume that the diffusivity is constant, but it is not true, you know. But the thing is, measuring the diffusivity is really hard. You know, the diffusivity changes over time. Also, since the material is changing, your diffusivity is changing also too. Also, during the depth of the material, also the diffusivity changes. Because at the first layer you have fully oxidized, then you have less oxidized, and you have intact fall. So the diffusivity of these layers are completely different. But how you can measure them is really hard.
So you're basically using an average diffusivity.
Average diffusivity.
All right, well, let me, one more.
This is a very important project,
Yeah.
because in terms of the whole United States, the efficiencies of these lines are like 99% or something like that. But if you could improve it by 1/10% for the nation, you would save a huge amount of fossil fuel or other fuel at the source. Small percentage of efficiency gains make big payouts.
Just to make a comment, this has the efficiency is more than the other one. But the thing is, the industry is so conservative. It's a new material. They don't change their line, right? And the other thing is, the cost of this one is almost twice as that one, the initial cost of it. But over time, you're going to get more benefit by installing this one.
Yeah.
One more, quick.
On the last few slides, you had two samples with two different colors, two different temperatures. I just want to know what's the cost for these
The
colors.
next one.
Which one?
A few more.
That was it.
Oh, this one?
Go more. Yeah, this one.
Oh, those are the same. Basically, those are the same. I think it's optically.
I thought you're
No. Those are
different
the same.
conditions, so it's not oxidized or something like that.
No, maybe I had to change it. But what I wanted to say is you see the exfoliation of the first layer of fibers. As you see, this is more at 200 degrees C rather than 180 degrees.
All right, well, let's thank you.
Thank you.